I'm Ankan. Actually was part of first cohort of PBA. So good to see how much it has evolved now. Um, yeah, and I work at Parity, same with Kian, as a runtime developer. Uh, and I'm going to cover scale, which I guess you guys already asked a lot of questions. So hopefully I can answer a few of them. This is actually, uh, one second. This is difficult. Okay, now we're good. Yeah, you guys already asked a lot of scale questions. Hopefully, I could answer a few of them. But these slides are actually from Sean, who will be here next week. Yeah, he's the genius guy. So hopefully, I answer most of it. But whichever I can't, I will try to get back to you. Yeah, let's go. Uh, Yeah, by the end of this lecture, you will understand why Substrate uses scale. You guys asked that a lot. You will also be able to understand like how different data types are encoded in scale. You'd be able to play with the blockchain, make sense of those hexes that you see all around. Yeah, and it also will help you actually make better decision as a runtime developer when you think about refactoring your data structures. Okay. So what is scale? Scale stands for simple concatenated aggregate little endian. Lot of words. It's an extremely lightweight format which allows encoding and decoding. It's meant for very resource constrained like execution environment, which is blockchain. There is a word called little endian there. It's the next slide. So it just determines the order of the bytes that we write. So when you write English, it's kind of like big endian. You write the most significant bit or most significant byte first, and then the least significant byte. So let's say imagine in the picture you have the 0A, 0B, 0C, 0T. That's hex number. And okay, I'm going to use this, but hopefully everyone can see me. And in a big endian, that is a normal general way of writing numbers. You write the most significant byte at the least smallest memory address. This is big endian, but in the little endian, you reverse it, you flip it. So you write 0A at the largest address, and like you go like this. Hopefully at the end of this lecture you will know why scale does that. It actually is written here. So Wasm is also a little endian system, and it has to do a lot of encoding and decoding to Wasm, and that's actually an advantage for scale to be little endian. Okay, and this was a good question in the last lecture. Why scale, why not X? There were good, actually, examples about that BCS, if I remember correctly. I actually read about it, and it actually sounded very similar to scale. I'm not sure about the technical aspects, but I think scale is kind of similar. I'll just go on with this, and hopefully I answer the question, why not protobuf at least? So yeah, scale is very easy to define, specifically for Rust context. So if you use a struct, or if you just use these macros, derive, encode, decode, and you get your encoding and decoding functions by default. We also use a few macros like max encoded len and type info. These help with giving some runtime guarantees of how big your data structure can be. And this is very important for a blockchain runtime, to have some guarantees how much computation you have to do. This type info that, as I think already Kian mentioned, scale does not retain type information. So this type info actually helps to us to generate metadata that helps another computer or server decode what you're sending in a scale encoded form. And the third point actually is why I think, I'm not an expert, I think why we don't go with protobuf. So, yeah, scale is no STD, it's a no STD like implementation, which means Wasm is also no STD, and we want no STD because there are some things in STD which are like not deterministic and difficult to use in blockchain context. Yeah, I think there is some implementation of protobuf in a STD with STD, but it uses some unstable features as well. So yeah, I think protobuf is out of question. Though BCS I think is a good tab in a.
Oh yeah, I was doing a little bit of research before the lecture right now started, and more or less, I think the main difference is that Scale more or less focuses on efficiency and speed, whereas BCS on itself focuses on type safety. And since you already have type safety with Rust, then you don't really have to worry about type safety with your serialization format. So more or less, you can just focus on the efficiency and speed for the actual format rather than just whether or not it's safe.
Okay. Yeah. Yeah, I don't know too much about it, and we can learn more. It's also learning for me. But when I read about it, I mean, I did see that they also don't retain type information, so it sounded a bit similar. Anyways, I'll just move on. So also, yeah, I mentioned it's deterministic, and that's what it says, bijective, which means the way you encode, when you decode it with the same type, it's always the same structure that you will get. It has one exception that I will cover later, but generally this is true. It's supposed to have copy-free decode in Little Endian architectures, which is Wasm. So because it's same format as Little Endian, it actually, you have copy-free decode. And it's as thin and lightweight as it can be. Okay. Yeah, we already have said few times that scale is not self-descriptive. Actually, Kian gave the exact same example, so I can go over. Yeah.
I'm missing why Little Endian is more performant.
It's more performant because the way it's written in the memory. So imagine if you go from a big Endian architecture to a Little Endian, you have to flip bytes, you have to do more work. Mm-hmm. But since we use Wasm a lot, and Wasm is also Little Endian, then it's easier for decoding and encoding.
So if Wasm was Big Endian,
yes.
Big Endian would, okay.
Yes.
Yeah, thanks.
I mean, there are some trade-offs. You can learn more about Big Endian and Little Endian, but I think this is what takes the cake in some ways. Yeah, this example is kind of, I mean, this has been told before. Scale does not retain type information, and it's the exact same example that Kian gave. I can quickly repeat again. Here on the left, we have it's scale encoded, and the other is JSON. JSON is kind of tricky. I mean, you can give whatever name. It can give a smaller name, and the length of the encoded value would be less. But the thing that to understand is, since there is no type information at all, it's strictly better than almost any, I guess, any encoding format that has type information in it. There's a question there.
Mauricio, so my question is on scale encoding. Why are there trailing zeros?
Why are
they are trailing zeros? Trailing zeros.
Yeah, good question. So, so try to encode this. So this is 1 byte. This is 1 byte. This is 4 byte. 1, 2, 3, 4, 5, 6. And then, okay, sorry. This is an option. So this is an enum. So I'll cover this why this happens, but there is 1 byte for enum and then 4 bytes for this. So there's 7 bytes.
1 byte for enum and 2 for the variants, right? No, like two variants, right?
I will go again. So 1 byte, 1 byte,
yes,
2 bytes, 1 byte for the enum, 3 bytes,
okay,
and this is 4 bytes.
Or U32 4 bytes?
Yeah.
Oh, yeah.
So it's 7 bytes. We will see more examples how every single primitive is encoded. So you will understand this more, but yeah, this is the basic idea. Okay, people who want to, and I would encourage to do it, I can take like 1 minute here. If you want to play with the examples that I'm showing, you can just create a new project, add this dependency with feature derive, and then you can actually copy the code that I'm showing, and you can experiment. You can change few things. You can, do things. You should also have the old slides with you, and you can copy from there as well.
Quick question, why is 42 represent as 42 and not encoded into hex or bytes? 42 or 69?
Okay, it might be actually a mistake. Yeah.
I mean, in JSON it is, because it's like
I think it's a mistake.
Human readable, but okay. Cool.
Good catch, yeah.
So it should be like whatever.
Yeah, it's the encoded form. We will see how 42 actually is encoded. There is more example of it. Yeah. Should I go on, or if anyone is trying to do this? Okay, I'll move on. Okay. Just to clarify how little and big endian outputs look, we will see some examples. When there is just 1 byte, so you see I8, which is a signed integer, 1 byte always stays same order. There's nothing to like order, right? The bytes are interchanged in the little endian. So little endian and big endian are same if there is 1 byte. Binary is always represented the same way. Imagine now you have 2 bytes, U16, and you have to represent 42, and now there is 42, which is represented as 2A actually. So it is the, yeah. So 42 is, if you try to count this, this is like 2, 4, 8, yeah. This is A and this is 2. So this is represented as 2A, and there are 2 bytes. So in a normal way, what you will write is 002A. Right? That is big endian. But when you write in little endian, you reverse it. You write 2A and 00. Make sense? Similarly, if we take, I think, the biggest integer probably, the biggest 3-byte integer actually, and then you try to write it in big endian, you append it with 00 in the forward, and then if you do it little endian, it's reversed again. Mic? Somebody? Who has the mic? That.
Why are there 2 zeros at the start?
Why are there 2 zeros? That's 1 byte.
Yeah, but you said it's the biggest number in biggest 3. Okay, got it. Thanks.
Did you get it, or? Okay, let's now cover some data types that are encoded into scale. The first example is 69, unsigned, signed integer. Signed integer comes as 45, the unsigned also as 45. So if you remember, we said that scale does not keep the type information. To actually decode it in the right format, you need to know the type ahead of time. So if you try to decode any of this, so if you take the encoded form of this and decode as U8, it's perfectly all right from scale's point of view. There's a mic? Microphone.
So what you're saying here, more or less, is that scale just more or less saves the critical information. So if let's say, for instance, again, for this example, you have a positive integer 69. That would just be encoded as the data value, hexadecimal value 45, basically. because it's a both for the unsigned and signed integers, they're both positive, so you don't need a negative
Yeah.
negative sign
Yeah. Yeah.
data value, more or less. If it was negative 69 for the signed integer, then you would basically store that. Would you store that?
Not really. I think so. You can try this example to be really sure. But I think what happens is you take 2's complement of, so you represent it in a binary. You take 2's complement of it, and that's how you represent a negative number. And the first bit kind of indicates that it's a negative number.
Gotcha.
Yeah.
Thank you.
What else is here? Yeah. Just okay. So I showed you fixed width integers, and if you see 42, when it is encoded with a 2-byte format, it appends 00, right? Makes sense till now? It's a fixed width integer. It always is 2 bytes. But there is a nice little feature for scale. We can store some integers in compact form. Imagine a data structure that can be really high, but generally is really low value. Then you don't need to store, let's say it's a U256. You don't need to store 16 bytes if it can be stored in just 2 bytes. That is what compact integers do, and it can support integers up to the power 536, which is extremely large number. I'll show you examples for it. Okay, and how does it do it? You don't have to learn these rules, and it's just for example, but the way it works, it uses the first 2 bits in a little endian form. In the big endian, it's like at the back. The first 2 digits are, the first 2 bits denote what is the range of the number. So if 0 to 63, it's 00, similarly for others. And I will show you examples of this as well. And also encode sometimes the length of it. So there are like details, single byte mode, 2 byte mode, 4 byte. So depends on these bits. It says how many bytes tells you like more information about the length of the integer. Mike, at the back.
Yep. So in terms of compact prefixes, so it kind of like also attached some context over the data being encoded.
Yeah.
In terms like, okay, maybe it's U256, right? And after compacting, it's like the prefix says like, okay, this integer is 256, but then the representation maybe it's only 2 bytes of it.
Yes. Yeah, you can think, I mean, it's a bit of optimization. Instead of keeping the exact length, it keeps only the range, and it is able to decode what is actually the length by just few information that we add to it. So an example, when you encode 0 or encode 0 as compact, there is no difference, except, yeah, so this is like 0 in 1 byte, and 1 byte doesn't, you can't compact it even more. But when you encode 0 in a 4-byte format, you have these many zeros, but in compact form, you just indicate with just 00. Yeah.
Is there ever a reason not to use compact?
Sorry?
Is there ever a reason not to use compact?
Not to use compact.
Like, why would you not always use compact?
So in worst case, actually, and I will show you a couple of cases. In worst case, compact can be actually larger than non-compact. But it's only few edge cases where it is. So it's like 99% time. So if you have a data structure where you think generally the data size varies a lot, and generally it's smaller, then compact makes total sense. But let's say you have a U32 and you think it's always going to be U32, like around 4 bytes. Very rarely it's 1 byte. Then you shouldn't really use compact. I guess it's not too bad, but it can be 1 extra byte. I'll show you why. Because it appends 2 bits, right? So it can be actually larger than that than the non-compact. I think this is not the example, but we'll get to it. So, imagine we encode 42 in 1 byte, 4 byte, as you expect. The interesting thing to see is that 42 in 1 byte or 4 byte is exactly same. And if you see it changed a bit. So how did it change? So you take the binary representation, you add 2 bits 0, 0 to it, I think at the backmost, because right now what you see is like big Indian format. Yeah, it's 2 zeros at the back, and then you get A8. Yeah. Did everybody hear the question? I can just repeat it. So he's asking in what context we should use compact and not compact, and it's the same answer what the other question was before you. Mostly compact makes sense when you think a U32 generally contains U8, like 1 byte data. Rarely it contains actually the full byte. And you can think of it as user balance. User balance needs to be supported, I don't know, like U256, but generally most users have very small balance. So imagine if you didn't use compact, it would be like 16 bytes for every account that has any balance, right?
Yes, my question mostly is on the representation of as compact. For example, for 42 U32, it's same A8, but then why is there no like prefix for it for the context?
Yeah. So there is prefix. I showed you there is. Yeah, there is prefix. So this 2 zeros that you see is the prefix that we added, and that's why it became A8.
Okay, the original is okay. No way. Okay.
So we take this binary, and then you append 2 zeros to it.
And then you, because it's into Indian, so it changes and.
So if you now calculate this value, this is A8. It's not 2A anymore.
Okay. So okay, yeah, sure.
So my question is, there are 2 options here to use just usual encoding or as compact. But during decoding, how can we like differentiate? Have we used as compact or just usual encoding?
Yeah, so I mean this kind of, so actually we have a workshop after this, and you will actually see how it is, how you can actually encode and decode, how can you know the type information. But to answer it briefly, in your runtime code, you will always have structs, and you will have like type as compact or nothing, which means non-compact. And every node has the same type, right? Or if you are talking with something like a browser, like a dApp, then you need to somehow give that type information to them, or the dApp needs to know the type information ahead of decoding it.
Thank you.
Same example with 69, and I think one guy asked about this question, and we'll get that answer. So 69 in 1 byte is 45 in 4 byte, 0 appended to it. In 1 byte format, now if you see, it has become 2 bytes. So it's actually strictly for worst case, it's bigger than non-compact. Yeah, and it's same. So there's also another thing. If you imagine you have a block number with some type you have given, maybe U8. For the example, U8 is too bad for a block number, but let's imagine it was U8, and you realized after 255 blocks, my blockchain is famous and people are using it, and you need to make it U32 now to support your blockchain for longer. You can actually do it in a very backward compatible way. You make it U32, and you don't have to migrate your data storage because it's actually same in the storage as it was with 1 byte. So it's backward compatible. Same example. I'm gonna just go forward. I think there's nothing too interesting here. Yeah, I already said it's backward compatible. Let's go to enum, how they are represented. So the first variant is always encoded as 00, and then you go like 0001, 02, 03. And enum can contain data itself. So if you encode first, you will get 00 because just enum. But for the second variant, you have first 01 as representing the second enum, and then 02 which represent the U8. So we did, okay, I don't know if actually that's correct, if two, okay, yeah, it's probably, I'm not sure. But the idea is that this is the enum variant and this is the number. Similarly for third, you represent third by 02 and then the actual vector. We will see how vectors are encoded in the later slide, but first the enum and then the actual contained value. And for fourth, it's same as the first one, 03, that's all. Is there a mic?
What is the 14 in the vector?
What is
encoding?
what?
The number 14 when it's encoded. The second from the bottom line.
We will cover that, but the short answer is vec are also like compact integer coded. So first you tell the length of the vector, and the 14, 5 I think is encodes to 14, and I think that's what it is. We will see this example later. Yeah. Is there a mic? Can you pass the mic?
Yes, my question is like, what is the mechanism behind when we are encoding certain types into a certain encode, numbers or maybe whatever digits it drives to, evaluates to, right? So for example, like you said, in the previous example, so some 69 goes to 45, right? So what is the mechanism behind? Is there something which is some strategy to decide that, or say encoding code the way it is written, that it encodes to certain bytes, certain format?
Yeah, so I mean, scale is like set of rules that we follow to convert some primitives into some values, and then there's a Rust implementation. So Rust implementation knows, okay, for this structure, it's a vector, stuff like that. Like so this structure, how do I decode into a vector? How do I decode into a struct? And sometimes if you don't give a correct type, it could give a wrong information, or it could actually be totally incorrect. It would look like it passed correctly in a some struct, but it's something else. So the parties who are exchanging this data, they both need to have the type information, the correct type.
Okay.
This will hopefully make more sense after the workshop, where we will actually do this exercise, where you will actually decode scale encoded data.
All right, thank you.
Yeah, tuples and structs. So kind of same thing that I explained to you. Scale does not know the type information. So imagine you have a struct with 3 fields, number is cool, optional, and you have the exact same type as a tuple. So you have the same thing as U8, bool, and option with a U32, and both will encode to the exact same value. Which also means actually if you start with a tuple in your data structure and you later want to make it like named in your code, make it in a struct, then it's backward compatible. You have to not do any database migration. Actually, if you change the names of any struct, doesn't matter. So few things you get. You lose the type information, but you gain something. Yeah. Is there a mic? Oh, can you pass it?
Yeah, so in the encoding of the struct example, so in the SAM 69U32, because it's an enum, and like checking there in the encoded format, we have okay 00 because of the like the first one, and 01 because of the true, right, the boolean true, and then we have 01 and then 45. Now that represent the enum option, right?
Yes.
And okay, 01, what it's what, and 45 it's
So 01 is for the sum variant of the option,
okay.
and then 45 is the encoded form of this 69.
Okay, okay, and then it's because it's 32 because of 4 bytes. Okay, and okay, what if it is none and not some?
What if it was 9?
None, as in some or none.
Yeah, but then you take the encoding of 9, whatever it is.
Not 9, none, N-O-N-E.
None. So then it will be, then the variant will be 00,
00, and then
and that's all.
Okay, 00 also. Like, okay, it will only be 00 and not like extra 4 bytes on.
I mean, you can check it. I think it will not, but
Yeah,
you
let me
can
check.
check it to verify. You have a question?
So my question is like, how important it is to understand the skill encoding while we are writing the runtime, while we're building the blockchain. So, so do we like have to have a proper like understanding or knows, remember the codes that okay, this particular type evaluates to this particular byte, so which is the smallest, I mean storage space, it takes the smallest storage space. So that helps to design the very optimized blockchain in that case. So do we need to, and how do we keep those things, like remember all those things, when we do that?
Yeah, so when you start, to be honest, you can ignore this. You can be completely ignorant of the fact that there is scale encoding. But knowing this makes you a better developer because you can make some decisions that will save you a lot of time and effort, right?
Exactly, that's what I mean.
Yeah. Like now you know that how struct is encoded. Now you don't have to be worried about changing the names of these fields, right? But imagine you have to flip a field. Then you know that's going to be like a huge data migration.
Thank you.
Yeah. Compact also can be embedded in another structure. So you can have struct and then embedded compact. And hopefully if you see the example, so what we do, we take my struct. Yeah. So in this case, you are embedding inside a enum. And then you see that without the enum, it's like it doesn't have the enum variant, but with enum, it's the same number, and you see this part after 2a, it's exactly same. So yeah, basically, if you embed it inside, it's totally fine. Okay, a few more types. Unit is represented as no bytes. True is represented as 01, false 00. Enums are always according to the way it is defined. So if you go and check result, I think, yeah, OK is the first variant and error is the second variant. So it's 00 and 01. I think somebody asked the question, right? What if the value is none? It's kind of similar here. When the value is error, and I think the second part is unit, you see it's just 1 byte, nothing else. Is it the same thing I'm looking at? Yeah.
Explain the fourth one. OK, U32.
Right. So OK is first variant, so it's 00. And then it's 42, right? Yeah. That's all it's encoded.
It's U32, right?
Yes. So when you say, okay, it's just trying to translate like what is the result type, that's all. But for error, there is no value, and then it's just 0, 1, nothing else. So it's saving bytes there. 42, you have already seen, it just appends 0, 1 to it. The variant information for none, again, just 0, 0, nothing, no data following that. Arrays, vectors, and strings. So arrays are fixed length. So we don't need to give any length information. We just append the numbers, that's all. All the integers are just appended together. For vectors, though, it's different. Vectors, we don't know ahead of time what will be the length. I mean, in this case, it doesn't make sense, but if you think of it in a struct where there is a vector and then there is something else, you need to know when to stop looking at the vector. So you need to give a length of it. So it's compact integer encoded, if I understand correctly, yeah. And the first, or is it? Yeah, so first byte represents the length, which is 5, I think, if I'm not wrong. And the following bytes are like those elements in the vector. Strings are exactly same as vector as far as encoding is concerned. So it's like vector of UTF strings. Yeah. Imagine also like you have a vector of like 1024 zeros. Again, now these 2 bytes, actually, if you follow the rules there, for the bigger length, there are different encodings. So this is 2-byte format, where you use 2 bytes to represent how big is your vector, and then append all the zeros there. You don't have to remember all this, but it's good to just go through these once. There's a question behind. Can you pass the speaker?
Yeah. On my question of the none and some, right? I was checking here. So with none, it ignores other remaining bytes. With some, of course, it adds with the U32. But one thing is, my concern is memory allocation. So early, okay, in enum, the memory allocated is for the like the largest variance. That would be like the memory allocated for it. So in encoding and representation of encoding, is it the same? Because as in some, it is much bigger, but the none is smaller. So we are memory like allocating the bigger one and accommodating the smaller, right?
Yes. So the maximum encoded size of an enum, you can think of the worst case where you have some everywhere, but it optimizes when it doesn't have to have extra information to understand that value, right? There was a question in the front.
Honestly, not very important question, but how 14 is 5?
Try to do this. I hope it's correct, but we can do this later. It might be a mistake, I don't know. You can check it. But ideally, the encoding of 5 should be 14. So if you, in the hex way, so if you're not writing 5 as an integer, but in a hex representation, it should be 5 as 14.
My question is regarding types, data types. Is it important the order of data types in structures, like during the encoding and as compact and so on? Like what I mean is, when we're writing a code, should we take into account that first we put a boolean, then integer, and so on?
Yes. So you need to know the type ahead of actually decoding the value. Otherwise, you can decode the wrong data. You might get into, so we will see some decoding examples as well. You might actually pass it correctly and get to a wrong value, or you could actually run into an error that this cannot be passed because it expected more data and the buffer filled before it. Things like that. You will get into some errors. We'll see some examples of decoding as well. Yeah, here we are. So we already said that whoever is decoding this scale encoded data needs to know the type information ahead. And we'll see some examples. So imagine you have two values, an array, 0, 1, 2, 3, and a value that is like 50 million, I think, yeah. The interesting thing is both array and value actually encodes to the same, exact same scale encoded data. Now, if you don't know the type, so imagine you take the array, you encode it, and the decoder decodes it into a U32. You actually get from array to this value. So it's important that you know the type ahead of the time, otherwise you can actually get wrong data. Similarly, if you try to decode a larger data, which is 4 bytes into 2 bytes, again you can get wrong data. You get 256 because it takes only the first 2 bytes. To circumvent these kind of errors, you can actually use another API, decode all, where it tries to read the whole thing. I'm not sure how it knows where to end, but I guess in this case it's easy. But in case where there is like embedded structure, yeah, I'm not sure. But for this case, it will tell you some error that it cannot fit. What does it? Yeah, exactly. It has more data than you allocated to it. There is another error where you have 4 bytes and you're trying to decode it into 8 bytes, and then you again get some error. Okay, so decoding isn't free. So when you are decoding, you have to do a lot of computations. You have to, sometimes it can be like loop as well, like where there are nested types. You'll see an example. And to make sure that we never run into Stack Overflow kind of errors, there is something called decode with depth limit, where it goes up to certain depth, and if it doesn't, if it's not able to decode by that limit, then it just errors. By default, the limit is 256. We'll see an example where this happens. So you can create like a decode bomb where, let's say you have an enum. You have one variant and the second variant that is actually itself. So second variant contains another example enum. And then you can have like, imagine you have this byte, so where you're saying second variant, second variant, second variant, second variant, second, first. So this is like a nested type decoding, and if you decode like just normally, it will decode pretty well, second, 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 first. Perfect, no problem. If you set a depth limit of 10, again, it's depth of 6, so it works fine. But if you say depth 3, then you get some kind of error that indicates something really bad happened. I mean, the default value is 256, which should be fine for almost every case.
If it's a struct with a vector and the vector has like more than 200, or what?
Sorry.
If it's a vector and the vector have more than 256, then we need to do the depth with more.
No, I mean vector is not. You're not doing nested. You are actually doing sequentially.
So that's only in the nested.
Yes.
Okay, thank you.
So you have like enum, inside that there is a enum, inside that there is a struct, things like that embedded. I mentioned in the beginning that it's not always bijective, as in deterministic. When you encode something, when you decode it with the same type, you should always ideally get the same value back. There is one exception, B-tree set. So B-tree set encodes almost not almost, it encodes exactly like vector. But and it can take an unordered set. So let's say you have this unordered set of 5 values. Again, 14 represents 5. 4, 3, 2, 1, 0, it's unordered, like in a reverse order. And when you actually decode it into a B tree set, it orders it. So now you encoded something else and you're decoding and getting some other value. Again, I mean, generally you will not make these mistakes, but it's not strict. I mean, there is a case where it's not bijective. With scale also, there are some optimizations we do, or we are able to do with the way scale works. So imagine you have to read how big is your vector, but you don't want to load the whole vector in your memory, right? It can be really big vector. You don't need to. You just read the first byte of the vector, and you know the exact size of the vector. Similarly, you don't need to decode the vector to append an item at the end of a vector. You can use something like encode append. You append an item without decoding anything. So scale is kind of inspired by Rust, but it's not Rust specific. So there are different implementations in different languages that have scale encoding and decoding support. And yeah, these are already, the presentations are already with you, so you can actually see the links if you're interested. This is also, I think, a good way to get a grant to write a scale library in the language that you want and get some money. Yeah, this question was asked a few times, like how does the receiver know the type information? We will see about this more, but every substrate runtime has a way to, so it's called metadata. It has a way to tell you what are the types that are stored in the runtime, what are the types that some extrinsic accepts. So you can get all the type information from this metadata file. So whenever you interact with the runtime, you download this metadata first, you keep this information with you, and then you talk to it with other things, and when you receive something, you use this metadata to figure out what type this is. Yeah, that's the end of it. If you have any more questions, I can take a few more. There's a question at the back.
Just want to be sure if I got what that means in the limitation of 256 is of nested items inside a struct?
Yes, so imagine there is a struct. Struct inside the fields is also a struct. Then that also has an enum and a struct.
So it's not the size of a vector, no. It's the nested item.
Exactly.
Okay.
Okay, thank you. I'm not